Okay. All right. So one thing I wanted to show you guys.
What was the intro?
Oh. Good afternoon, everybody. Class recording has started. There it is.
Yeah!
All right. One thing I wanted to show you guys is not that one, but here. Okay. I've shown you this before. It's been a while. We haven't used it too much this year, but you will get a clean copy of the physics data booklet when you take your exam. So
Mine has notes.
no, you will get a clean one. Don't worry. So you will get a clean copy of the physics data booklet. So in it, like I said, obviously it has a table of contents here. So we're working through the core right now. So we'll just kind of go there. Obviously, not obviously, but so the first page here, it's got some mathematical equations, right? Area of a circle, circumference, surface area, volume, all those fun things. A bunch of physical constants, right here. The one we used yesterday was our acceleration of free fall, 9.8, even though we discussed the idea that, especially if you're doing multiple choice questions, 10 is obviously a quick approximation that makes your math a lot easier to do, but if you're doing calculations, you probably should use 9.81. And then you got your metric prefixes, your unit conversions, and then we get, electrical circuit symbols, we're not there yet, and then we pick it up here with the core, right? So, here's our uncertainty equations that we went over before break, right? If you're adding numbers together, you just add the uncertainties together. If you're multiplying or dividing, then you add the fractional uncertainties together to give you the fractional uncertainty of the answer, and then power is a different thing here. Here's just your trig functions using sine, cosine, tangent. Yay. All right, so here's section 2, or here's part 2 on motion, right? Here's all of our Subot equations, right? We said that v is final velocity, u is initial velocity, a is acceleration, t is time, and s is distance. So we used that yesterday in class. For section 2.2 on forces, right? Here's F equals ma, that's your Newton's second law, and then here are your two equations for the coefficient of friction. S stands for static, D stands for dynamic, but it's basically the same thing, right?
I love this sheet, and it actually helps with a lot of multiple choice questions. Like all of the multiple choice questions, you just have to know how to work the equations out.
Pretty much.
It's awesome.
Here's work, right? We talked yesterday. Work is force times distance, but then we also talked, and we saw in a problem yesterday, that we only do the component of force in the direction of the movement. That's the cosine theta part. We didn't get much into kinetic energy yesterday, or potential energy, but we'll do a little bit of that today. Power is force times velocity, which you can also have it as work over time, which we used yesterday as well. Those are two equivalent expressions. And then finally, right at the end of the period yesterday, I think we did some impulse momentum stuff, right? That's our expression for momentum. Here's our expression for impulse. And I bring that up because the last question on the sheet today is an impulse momentum equation. So, with that, let's go here. So it says, a net force of magnitude F acts on a body, define the impulse of the force. Well, just going back to this, right? Impulse is equal to force times time, right? But when it says define, I don't know, you probably could just get away with force times time, but also too, more importantly, as more of an explanation, impulse causes a change in momentum, right? So this is only a 1-point question, so they're looking for a pretty succinct answer. You know what I'm saying? Like, they're not looking for a big explanation. I'm thinking either one of those would probably get you your 1 point. So
I would have put like changing momentum.
I think that would be fine.
All right,
so
cool.
so yeah, like I said, define is very succinct as far as the answer goes. Right? We're not looking for a big explanation. All right, it says a ball of mass 0.075 kilograms is traveling horizontally with a speed of 2.2 meters per second. It strikes a vertical wall and rebounds horizontally, right? So it's just coming in here, and then it's bouncing off the wall in the same direction, or the opposite direction that it came. It says, due to the collision with the wall, 20% of the balls 20% of the ball's initial kinetic energy is dissipated. This question right here, I have seen at least on 3 old tests, right? So here it says, show that the ball rebounds from the wall with a speed of 1.97 meters per second. It's giving you the final answer. It's asking you to show how they got the final answer, right? So if it's asking you, right, if it's saying that 20% of the ball's initial kinetic energy is dissipated, what do you first need to know? Well, find which kinetic energy?
The final kinetic energy.
No. Find the initial one first.
Oh.
Right? And then times it by 0.8 to find out 20% dissipated, right? Yeah, it's not a hard problem,
Yeah.
but interpreting what it's telling you, that's the important part, right? So, find kinetic energy, right? Do you remember the formula for kinetic energy? 1/2 mv squared.
There we go. You
That's
said.
obviously, that's gonna be in your packet, right? I mean, you know, there it is, right? Okay. But, so, now in this case, right, we said that we want to know what the ball's initial kinetic energy is, right? So we need to include that as the initial velocity, right? That's how fast it was going before it ran into the wall, right?
Oh, so we already have the initial. Or no, we don't have the initial.
What?
Jace.
We don't have the initial what?
We do not. No, I was gonna say we don't have the initial kinetic energy, but I said something wrong.
We do not have the initial kinetic energy, but we have enough information to
solve
calculate it, right?
Yeah, it just gives you basically everything. So. I would whip out my old calculator here.
Good plan.
Whip out the old number tiger.
Do you want this one? It's behind your bag. Don't push your bag forward. What do we get? We get 0.1, 0.1875 or something like that? 1.5, right? And then, so that's the initial kinetic energy, right?
Yeah. So we have
But
that.
it's saying show that the ball rebounds from the wall with a speed of 1.97. That's a rebound, right? So that's the final. So we know that 20% of the kinetic energy is dissipated, right? So Yusuf, who said, what are you going to do with this number?
Just says equal to the.
Wait, it says speed.
Oh no,
though.
times 0.8 and then says equal and then.
But it says speed now.
Okay, so, right, here's the deal, okay? We can't just take this number and multiply it by 0.8, right? Because kinetic energy doesn't depend on speed directly, it depends on speed squared, right? Do you understand where I'm going with this? You can't just take 80% of this number, because you won't get this number,
Yeah.
okay? Because, like I said, speed is not dependent on, or sorry, kinetic energy is not dependent on speed directly, it's squared in that formula. So if it's saying 20% of the ball's initial kinetic energy is dissipated, you need to know how much kinetic energy it had initially, and then there's only 80% of it left. Does that make sense?
Yeah.
Okay. So then, what do we get when we?
I just kind of do it real fast.
Okay.
Point. Right.
1452. So this is kinetic energy final, right? But it doesn't ask for kinetic energy final, right? It asks for the speed, right? So then, yeah. That's how we rearrange that equation to get the final velocity, right? So we know the kinetic energy, right? That would be this. We know the mass is still this, so we know everything in that equation. And when you plug it all in, you should get 1.97 for the final velocity.
Oh, I see. So just because it says speed, what you want is the force, and then you can maneuver, or you want the kinetic energy, and then you can maneuver it around.
Right, because you can't just do this calculation with the speed, because kinetic energy doesn't depend directly on speed.
That makes sense.
All right, good there?
It has
So
made
for
sense before.
part
It's appreciated.
2, it says, show that the impulse given to the ball by the wall is 0.313. So we said that impulse, right, is force times time, but we also said that impulse does what?
It's the change in momentum.
Okay, so the change in momentum, right? We don't have a time anywhere in this information, so we can't multiply the force by the time. We don't have a force anyway in there. But we do have a mass, we do have an initial velocity, and we do have a final velocity,
So we
right?
can calculate momentum.
We can calculate not just momentum, but
But the change in it,
change
you
in
multiply
momentum, right?
you multiply both of those together.
no,
Like, I'm bad at explaining things.
right?
That's why I'm not a
So
teacher.
we're just gonna do this.
Also, because I'm 18. Everything in Planck's constant. Oh my god, what are you?
Something to keep in mind here that's important, especially in this, okay, and they'll, again, doing in some of the examples that we've already gone through, I've seen a problem similar to this already. This tells you that this is a speed, right? But, say again? Not units, but momentum is a vector. So direction is important, right?
Oh, so
if
positive,
this,
negative.
So if this is going this way, this one is gonna have to be going this way. That means one has to be positive and one has to be negative, right? When you calculate the change in something, you always subtract it, but these numbers could be positive or negative.
So to
And
find
we're gonna end
momentum-
up actually being
Going that way.
right, so.
Momentum is speed
That's a tricky one.
times
That shows,
mass.
anytime there's a bounce, you have a change in direction, and so, in this case, Austin, do you wanna call the way the ball is traveling initially positive or negative? Yeah, so this is gonna be positive, and that means that this one here is gonna be negative, does that make
Yeah.
sense?
Because it has to
So,
be
to calculate momentum, do we remember how we calculate momentum?
mass times speed.
Mass times velocity. That's a-
Same difference.
No, not in this case, it's not.
Oh yeah, because it's actually.
Right, so we multiply mass times velocity, but that means this final velocity or final momentum is gonna be negative because we have a negative velocity minus a positive initial momentum, that's gonna give us something bigger. You know what does that make sense mathematically? Right? Good. That's an important one with the bounce, because it's gonna change direction, that changes the sign, and that changes that calculation. Like I said, this problem we've seen at least once, so. Okay.
I'm pretty happy with what's going on right now. Like, I'm not confused.
That's good. Do we need a number to finish this off? Oh, well, it should.
Yeah,
Yeah,
I
it's
would
just
say
gonna-
these things would be like,
right? It says, again, show that the impulse is that much, so you should get that much. Now, if ours comes out negative, that's okay, it's just the direction that we chose. All right, good there?
yeah.
So then for part C, green for this one. It says the ball strikes the wall at time t equals 0 and leaves the wall at time t equals t. The sketch graph shows how the force that the wall exerts on the ball is assumed to vary with time. Time t is measured electronically to equal 0.0894. Use the impulse given in B2 to estimate the average value of f. This is actually a super simple problem. So, okay. So, that's part of this. Don't get confused with all of this stuff, right? What is this problem actually asking you to do? Average value of f. It wants to know the force, right? Okay? That's what this problem is asking you for. Okay? What did it give you?
Sketch graph.
It gave you the sketch graph.
underneath the sketch graph, what did it tell you? And it's not a length, it's a what?
Time.
It's a time, right? It says the time is measured to equal 0.0894 seconds.
Yeah.
So we have time. Yeah. In the previous problem, it even tells you, use the impulse given in V2, right? It tells you in V2 that the impulse is this much, right? If you know the impulse and you know the time, can you figure out the force?
Yes.
How do we figure out impulse?
I equals F delta T.
I equals F delta T.
Yeah.
That's a terrible I. And you know 2 out of those 3 things.
Oh.
And you honestly didn't even have to calculate any one of them.
Yeah, because initial, final, changing time is just gonna be whatever the final is that you already have.
Because the initial time in this case is what?
0.
0.
So.
So final
yeah.
minus initial is just whatever you end up with there, right?
So the sketch
You don't
graph-
even have to figure that out though. They flat out told you the time is measured to equal that much.
And the thing is it's like the sketch graph is kind of unimportant.
It's totally unnecessary in this problem.
The only thing it does is kind of hint at the initial velocity, or initial time.
Yeah, but
Otherwise, it's completely useless, and it.
so again, that's kind of like the
Yeah.
zone out, like all this
It's kind of like scared, so I was trying to.
yeah, like all of this
It's so unimportant.
is completely unnecessary to do this problem.
More
Right?
unnecessary
So
than government.
keep it in mind, right? What, make sure we're like, okay, what is this question actually asking me for, right? It's asking me for force to estimate the average value of F. It gave me the time, and it said use the impulse from the previous problem. I think they're trying to test your ability. Like, this is more of a problem-solving activity, I think, than actually your ability to calculate force. You know, so can you pick out relevant information? Can you identify what's important to us?
That's all that matters in the end.
So, all right, how's that? Good there.
Yeah.
All right, that's mechanics. Good.
Mechanics are a really underrated job.
All right, so the next thing, yesterday I gave you guys, I sent you guys the information on the thermal physics stuff, right? It's kind of a long package, so I don't know if you actually read it or not, but let's start. I should probably give you guys the questions that you can go through, so.
I'm actually pretty confident right now.
That's good. That's probably only like.
That's until we get
That's
to
the stuff we did over yesterday is probably only one question on the test.
yeah.
So it's good. We at least got one question.
Electricity and magnetism is what really gets my gears grinding.
That's chapter 4. So
Yeah, that's where I die.
that's where we're going next. All right.
Mechanics,
So
thermal,
thermal physics, right, talks about energy, but it talks about heat energy and then what that does to things, right, especially the particles that make up a substance, right? A lot of this section is chemistry stuff. So some of it may look familiar from chemistry, you know, depending on how much of your chemistry you remember, you know. So. All right. So this first one, it says the substance is heated at a constant rate of energy transfer. A graph of its temperature against time is shown below. So this is a temperature graph of a substance that is being heated. Notice, right, there are 3 slanty sections and 2 flat sections. Do you recall what the flat sections on a temperature graph relate to, or phase changes, right? Okay, so flat sections are going to be phase changes on a temperature graph, right? So this object starts in what state of matter? Even though it doesn't tell you, we can figure this out, what state of matter it is.
Solid.
Starts as a solid, right? And then from L to M, it's doing what?
liquid, gas.
It's melting from L to M.
Oh, I thought you meant from
right?
K to P.
No. I said from L to M. So,
I know, it was a little off.
right?
My
And then that means from N to O, it's doing what? It's vaporizing or boiling, however you want to say it, right? Okay. So, which regions of the graph correspond to the substance existing in a mixture of two phases? When is there going to be a mixture of two phases? When it's doing what? Yeah, when it's doing B, yes, right?
LMNO.
This is going to be the answer here, right?
LMNO.
Because L through M and N through O are the two phase changes on the graph, right? And if there's a phase change going on, there's going to be a mixture of different phases. Okay? 2, which region of the graph is the specific heat capacity of the substance greatest? I wish Fuad was here because he did his internal assessment on this, but right. So, do we have any recollection of specific heat capacity, or
How much
Specific
it takes
heat
to change
capacity.
it, like
how
1
much
degree.
it changes? How much it changes? How much energy it changes to change, or
By 1 degree Celsius.
or more generally, how much energy does it take to change the temperature, right? So in this case, if the heat capacity is the greatest, do you have a question? I couldn't tell if you wanted to answer my question about heat capacity or not. I didn't think, but I thought I'd give you I thought I'd give you the option. So
Is it OP?
it is OP, yeah. So okay.
Because a little gas.
Because, well, if we talk about the amount of the specific heat capacity is how much energy it takes to change the temperature.
Yes, why would it be MA?
Because in this case here, right, how much is the temperature changing compared to a lot? And that means the heat capacity is
Is low.
lower.
Really?
Does that make sense?
Yeah.
So heat capacity is how much energy it takes to change its temperature.
Right.
1 unit.
So
Oh,
a
got it. So
high heat capacity means it's harder to change the temperature.
yeah, that would be Optimus Prime.
Here's on the top. Oh, wait, no.
That would be Optimus Prime at the top. of the front.
If we go this, right, 'cause we'll come back to this equation, right? Right? Okay. And then if we rearrange this,
MCAT. Q equals MCAT.
right? Okay. In this case, we have a fairly low temperature change during OP compared to the other two sections, right? And if this is lower, what happens to C? It's bigger, right, because we have the bottom of the fraction thing, right? So in this case here, that would have the greatest.
Then also could you say the temperature is highest over there?
It doesn't, where it is on this axis isn't as important as the slope. Because the heat capacity is
Oh, wait.
energy per temperature, and even though this doesn't have temperature or energy on this graph, right, if it's a constant rate of energy transfer, the amount of energy added per second is the same. Does that make sense? Right? So heat capacity, because it's a comparison of this to this, on a graph would be slope, because that's what slopes do, right? They compare two things. It's a ratio of the two things. Does that make, is that good? Good on these two?
Yes, sir.
Alright. When the volume of a gas, section 3 also gets into gas behavior of gases as well.
Oh, like, yeah.
And so when we're talking about gases, there are basically 4 things that we need to know. Pressure. Oh, come on. Pressure,
Temperature.
temperature, volume.
And if they're all increased high, it's pretty kind of zero.
Moles.
That's
Let's go!
how much we're talking about, how many molecules we're talking about.
Bring it on, mate.
Talking ideally is about the relationship between those things. But when we're trying to describe the gas, we need to know what is the pressure of the gas, what is the temperature of the gas, what is its volume, and then how many molecules or how many moles of that gas there are.
They're like a constant to that.
There is a constant, we'll get to that. Yeah, it's R, it's the R
Moles.
value. And so,
Yeah, that's K.
Oh, no.
Well, it actually has both in it, doesn't it?
Oh, yeah.
it's different, so.
P equals
Okay.
MC.
This relationship
P
is
equals-
how those 4 things relate together, where P, E, N, and T are what these things are here, and then R we call the universal gas constant. It's a constant value that, relates there.
That's 5.
Say again?
It's 5.
Acceptable. Well, I
Bad.
suppose. All right, so it says, when the volume of a gas is isothermically compressed to a smaller volume, the pressure exerted by the gas on the container walls increases. First, does that statement make sense?
Yeah.
Don't get,
I just said it.
be honest if it doesn't
V
make
gets
sense.
big.
Right?
When the volume
Well,
is-
this
Yeah,
gets
'cause on
V,
the-
actually
on
V
that
gets
side.
what?
It's small.
V gets small,
So V
right?
gets big.
Okay.
It makes
So
complete
P has to
sense.
get bigger. And, right, don't get thrown off by the fancy words. Isothermically just means what? Well, what does iso mean?
Isolated, alone.
Alone, not the same. Or sorry, isothermically means the same.
So they're just trying to like
Say
throw
again?
more like.
No temperature change, right?
So they're-
So that means over here on the right-hand side of the equation, right,
It's still in the same system.
the number of moles didn't change, R is a constant, and T didn't change. So that means both sides of these equations have to be the same. If V goes down, what has to happen to P?
It goes up.
It goes up, right? And that's what it says, okay? The best microscopic explanation for this pressure increase is that at the smaller volume, blank. What causes the pressure that a gas exerts on a container? Collisions, right? The molecules run into the wall and they bounce off of it, right? If we have gases moving in a smaller space, how many collisions are there going to be? There's going to be more collisions. We can also make the pressure go up if we keep the volume the same and the temperature increases. Because what does temperature tell us? Average kinetic energy, how fast they go, right? So in that case, if we kept V the same, but increased T, mathematically, what would have to happen to P? It would have to go up too, right? But then, from the microscopic explanation, that would be because higher temperature causes the molecules to go faster, they run into the wall more often. Right? That's not what that question's about, but we could, just relating those things together. All right, good there? A lead bullet is fired into an iron plate. If we had gun control, if we had gun control, this problem wouldn't exist. Not like the problem of guns, this actual problem on the test would not exist. Where it deforms and stops. As a result, the temperature of the lead increases by an amount delta T. For an identical bullet hitting the plate with twice the speed, what is the best estimate of the temperature increase?
It stops dead.
Yep.
Is it 2 the same magnitude?
It dies.
Does
Not
look
B
like
or C.
does indeed look like there are two of the same answers. My guess is that B is actually supposed to be the square root of 2.
It's that one.
There's a reason why that is.
That one.
But I will tell
my guess, D.
D is the correct answer.
Oh, okay.
So, Graham, do you want to explain or do you want me to explain?
Just square energy, squared.
Right? Temperature relates to kinetic energy, right? So twice the speed is 4 times the kinetic energy because of the 1/2 mv squared relationship. Does that make sense? And so that means that the temperature would actually be 4 times higher because it has 4 times as much kinetic energy. Good?
Good.
All right.
I miss Hana.
So
Why'd she have to go? She said she
said she had to go to her counselor. Okay.
sounded pretty tricky, so.
All right. So
Probably
this
home.
this problem is the weirdest problem ever. All right. And it's in a way it's easy, but in a way it's kind of hard. All right. So I'll tell you let's go through it, and I'll tell you why it's kind of hard, but then why in the end it actually kind of turned out to be an easy problem. Okay. So it says, in winter, in some countries, the water in a swimming pool needs to be heated. Estimate the cost of heating the water in a typical swimming pool from 5 degrees Celsius to a suitable temperature for swimming.
Okay, 6.
You may choose to consider any reasonable size of pool. So what do you have to do to start this problem?
Big volume.
Make up a bunch of stuff,
Yeah.
alright? So, I'm not gonna lie, I looked in the back of the book to get the numbers that they used,
Okay.
alright? So, and you'll notice, right, here, right, if you look,
For the pool. Decide
you
what-
get
Choose your own
you get
adventure.
4 points just for deciding what the pool looks like.
You're
Oh, man.
freaking kidding me.
I'm there.
Alright?
4 points.
You get 4 points just for deciding what kind of pool you want to use, alright?
If
So,
you want a square pool, turn to page 15.
I wouldn't use square.
Choose your own adventure.
I want a sphere pool.
I
in
want my pool to
in
be
the
comfortable.
book, these are the dimensions that they
I
chose.
want my pool to be shaped like a dolphin.
20 meters long, 5 meters wide,
This is so random.
and 2 meters deep.
That's a really like.
Nah, 20 meters. Well, the pool at like the pool at like the YMCA, like if you, when you do laps, that's a 25-meter pool. So 25 meters long. So it's a little bit smaller than that, but it's definitely not. The pool at the YMCA is definitely more than 5 meters wide.
Which YMCA?
Like in West Park or West, whatever the one in West Lake is called. West Shore.
Does it have a pool?
Yeah, it has a pool. It's pretty small, but.
Ew.
All right.
Have that one for the next.
And then one more thing that we have to do here. What else do we have to decide? What is a temperature that is reasonable for?
6 Celsius.
That's pretty cold. It's cold. That's a cold bath. So, room temperature, generally speaking, room temperature is around 20 Celsius. Yeah. And so, you generally want the swimming pool to be a little bit warmer than room temperature. So in the book they chose 25 Celsius.
I love how they're just like, you can do what you want, we'll give you points for trying. And I get cool, right?
In the book they use 25 Celsius.
This is probably so people don't like totally die in the test.
Okay. Good there? Alright. So, what does it say? Estimate the cost of heating the water in a typical swimming pool. Okay? So in the end, we need some money. That's going to be our final answer. Okay? Here, they gave us, alright, a kilowatt hour of electrical energy. Okay?
So if we're heating the water, we're assuming that it's like a good transfer of energy.
That's one of the next questions actually, right? But in this case, we can assume that, alright? Kilowatt hours of energy, okay? So kilowatt hours, kilowatts is 1,000 watts, yes? Which is 1,000 what? A watt is what? We talked about this yesterday. Joule per second, right? And so this is 1,000 joules per second for how long? An hour, right? So here, this cost corresponds with 1,000 joules per second for 3,600 seconds. Does that make sense? Right? So 10 cents correlates with 3.6 times 10 to the 6 joules.
6:30.
Does that make sense that all those conversions I just made right there?
Let's see.
Oh.
Really sarcastic. Never mind.
So 10 cents is what it costs for 3.6 times 10 to the 6 joules, or 3.6 million joules. Okay? Now, what do we have? What?
It's not bad.
It's not bad. You don't think it's that bad.
Alright.
right? Now, what do we need to know? Right? We know that this is how much 10 cents is how much this much energy costs, but what don't we know yet for the pool? How much energy we need to heat the pool up, right? We can figure out how much energy we need to heat the pool up by doing this, right?
Cat. Q was on cat.
Yes.
A very difficult cycle.
All right, so two of these terms are pretty easy. One of them is a little bit trickier, right? Okay, so they gave us the density of water. From this, we can figure out what? Well, technically we figure out the volume of the water, but if we know the volume and we know the density, then we can figure out the mass, right? So 5 times 20 times 2, not mistaken, 400, or 2,000? Yep. I can 20, wait. It's 200. Wait, is it 200? Yep. Yeah, it is. Okay. 200 meters cubed, right? That's the volume. Okay. They give us the density, but we don't need density in this formula, we need mass, right? So if we rearrange that equation, right, you can figure out the mass by multiplying the density times the volume. And that should give us 200,000, right? Okay. So we can plug 200,000 kilograms in there.
Whoa, this is gonna be expensive.
It's actually
Wait, is it expensive?
it's actually not that expensive. That's so then they gave you the specific heat of water right here, 4,186. And then, right, in order to raise this up to 25 degrees Celsius, that would be a temperature change of 20 degrees Celsius. And plugging that all in, I ended up getting 1.67 times 10 to the 10th joules. Does that make sense? Okay. And then we know that this is how much total energy we need. We know that this much energy costs 10 cents, right? So what are you gonna do?
Portion!
Just divide, right? Divide this into this, and we find out that there is 4,639, and those would be kilowatt hours.
Times
Okay.
10 cents.
Times
So
10
110
cents,
would be
right?
4,630.25. For that. For that one.
$464. Now,
Isn't there 4 significant digits like that?
technically there's probably, well, there's like one here. Yeah, with this much going on, I doubt they're gonna take any points off for sick days at that point. Okay. So, as a parting shot, right? What's the problem? There's two problems with that calculation. Well, with the assumptions we made while doing this calculation. Nothing's lost to the outside, right? If you're heating a pool up in the middle of winter in some country, what's going to happen to the water as you're heating it? It's going to evaporate, but also it's going to cool off because it's right next to there, right? Okay. And two, what else did we assume?
Energy
Like the
perfect
measurements that are
transfer.
perfect or something?
True. I was thinking, how many times did we heat this pool up? Once, right? And that generally doesn't cut it as far as swimming in the winter time goes, right? So, all right, good job today, everybody. You know, we made some progress. We'll finish up the thermal stuff tomorrow, and
Here, we
then
actually have one.
get into waves is the next section. So we'll probably do some waves next. Okay?
Alright.
See ya.
Yeah.